Thank you, Scott. Good morning. I'm Anay Vardia, President and CEO of American Standard Circuits. We are proud to be one of the sponsors of the PCEA. I would like to do a quick introduction of ASC for those of you who are not familiar with us. We are a Chicago-based PCB facility focused on collaborating with designers as early as possible in the design phase. Our customers typically have fewer design and production issues because of this partnership that we create. We are a total solution provider focused on a wide range of technologies. We do digital, flex, rigid flex, RF microwave, HDI boards, and metal back boards, both RF metal back and insulated metal printed circuit boards. We provide both quick turn, prototype volume, and volume production. So we really do the entire range of technologies and the entire life cycle of the product. And by the way, if you're going to be at PCB West, we will be exhibiting there and would love to meet with you in person. We do have a number of free resources that are available from American Standard Circuits. Again, consistent with the education of the design community, we try to do that also. So we do have a number of resources on our website. So if you go to our website, www.asc-i.com, and look at free resources, you get sections on webinars, ebook, expert blogs, online DFMs, a whole bunch of different kinds of short video tutorials. So something that could really be of interest to you from an education standpoint of view. Again, as I stated earlier, if you're really working on a difficult design, we would love to partner with you to make your life easier. We do have a number of free ebooks from American Standard Circuits. So again, these are all downloadable from our website. And then as we come to the technical part of the presentation, so today we will be discussing two topics. We will be discussing the Averatek A-SAP process and the VFO process and a variety of options. So we're basically focused on HDI technology, and that's how we decided to kind of add these two what might appear disparate topics together. Joining me today are John Bushy, our Technical Director at American Standard Circuits, and Haris Basit, the CEO of Averatek. I will now turn this over to John to start the technical part of the program.
Thank you, Anay. We're going to start off talking about the A-SAP process, which is a next generation line and space capability technology. Basically, I think this is Haris's presentation.
Oh, do you want me to speak here?
Yes, please.
Okay, I can. So the subtractive processes are, as it says there, pushing the limits, mainly because they are limited by etch capability. And etch capability has not advanced nearly as much as things like lithography capability. So as you can see here, this is a fairly complicated subtractive process with multiple lamination cycles and is fairly significant layer count. And so A-SAP, the Averatek semi-additive process, is designed to simplify this and get much higher density on each individual layer or several of the layers. Okay, so the subtractive process, I think everyone is familiar with that. And the thing to, I guess, really focus on here is the part where we're etching the traces. So from step 4 to step 5. And you can see there that, of course, it etches, it undercuts a little bit, gives you a trapezoidal shape. And it's really the ability to control that etch that limits the width of that trace and also the space to the next trace. And you end up with traces that look trapezoidal like you see in the 6th image there. So in contrast, A-SAP works very differently. And the process is spelled out here, but you start with a substrate without any copper on it. And that might mean that you've removed copper that was originally there, that was laminated. And then on the bare substrate, you can apply a special chemistry, which I'll talk about later. You see it there in sort of that pinkish, purplish color. And what that allows you to do is it allows you to form a very conductive yet very, very thin electroless copper layer. And the key here is that it can be extraordinarily thin, a fraction of a micron thick, and yet it's still thick enough to use for electroplating. So then on top of this, you put the photoresist, you expose and you develop it. And then when you look at slide 6, what you can see is that opening in the photoresist, that tells you everything about what the trace width is going to be, what the trace height is going to be, because you're going to electroplate using the electroless copper as an electrode into that open cavity of the photoresist. And as it shows in image 7 there, you won't go quite to the top because you might go a little bit over, and that should be a problem, but just almost to the top there. Then you strip off the photoresist, and now you're left with a very, very thin electroless layer everywhere and traces where you want them. So the next step is to just sort of etch off that electroless layer. And so we call this semi-additive, and A-SAP stands for Averatek semi-additive process. And we'll talk more about it later, but you get a very rectangular, very rectangular cross sections. Okay, simplify the design. So basically the goal here is to put more density of traces on the A-SAP layers. What it allows you to have fewer layers, possibly a smaller footprint for the board, and also reduce the number of lamination cycles that you need. So there's a comparison here. This is actually, I think, from a real design that was done, where it started off having 12 layers and 4 lamination cycles. And you can see also the PCB size there in inches, roughly 5.5 by 5.5. And we redesigned it in A-SAP, and it shrunk the size of the board, reduced the number, so that increased the number that you could put on a panel from 12 to 36. So you get 3 times as many of these boards on a panel. But the layer count also dropped from 12 to 8. And actually, if you think of the layers that are dedicated towards signals as opposed to power and ground, that was a very large reduction in that number of layers in terms of percentage. And then the lamination cycles went from 4 to 2. The other thing to think about here is that it's not an either or. You can have a board that has, and most of the boards will be like this, have several subtractive layers, maybe for power and ground especially, and then a few high density A-SAP layers for signaling. Okay. So I think this is when I thought I was going to start, but let me start again. Actually, I didn't realize there were going to be 85 people online like there are now. If I did, I probably would have combed my hair before doing this. So anyway, I'm not sure if that joke goes over so well without me being on video, but anyway, I'll say a little bit about Averatek. Averatek is not a printed circuit board manufacturer. We partner with companies like ASC, who are printed circuit board fabricators. And what we do is we manufacture chemistry and we license manufacturing processes around that chemistry. And A-SAP is the first one of those manufacturing processes that we're putting out. We are targeting ultra high density printed circuit boards. And with that ultra high density, you can also get significant performance benefits in many cases. We have advanced technology in the lab that is looking also at using the type of equipment that you would find in a printed circuit board shop to package substrates and interposers and effectively allow even more aggressive layers that would let you embed bare die that have just pads with no bumps into what could be called a printed circuit board at that time or a package. We're also looking at very high frequency components like John's raising his hand. John, did you want to say something? Oh, okay. So anyway, high frequency components that like capacitors, inductors, and antennas that can be embedded within a printed circuit board and add high frequency performance as well. So let's talk a little bit about the chemistry which enables this process. We call it liquid metal ink, and we do that because it's a liquid and it has no solid particles in it. It does have molecules in it that are in solution. Those molecules are organometallic molecule. They've got a metal atom of palladium typically, and some organic part. And this molecule is designed such that it will not form bonds with or attach to other similar molecules. So it is in solution, it's floating free in the solvent. And we can put a very high density of these molecules into the solvent. And that allows us to dip a panel into this ink, or to spray the ink onto a panel, or there's a number of other ways to apply it. Allow the solvent to dry, and then cure it so that the organic part is driven off. And what you end up with is a very pure metal layer, palladium in this case, which is used as a catalyst. And it's very thin, just a few atoms thick. And it's also a solid film. The palladium atoms are just packed up against each other and cover almost any surface topology that you can throw at it. So that's the key advantage in this. So let's just compare how that looks. The liquid metal ink is on the right there, and it shows palladium in red dots, and that shows a layer of palladium, just a few atoms thick, that covers everything. And it's also and so it covers everything. If that surface weren't flat, whatever contours were there would be covered by the palladium red film there, and it would also form a continuous film. You can see that it covers that little opening there. We've done this on silicon wafers and shown that we can uniformly cover openings as small as, I think it's 25 nanometers in size. So very, very small openings compared to anything you see on a PCB. And because that palladium is a solid film, when you do the electroless layer of copper shown there in sort of that, mustardish color, it forms also a solid film, even though it's very thin. So typically the thickness of the electroless copper that we use is anywhere from 1 or 2/10 of a micron to about half a micron in thickness, depending on the size of the panel. So that contrasts with what you normally get when you use palladium for an electroless process, which is shown on the left. There you can see that there's large particles of palladium. Now they call them nanoparticles or other things, but there's still many thousands of atoms in size. You can't put a very high density of them in the solution, otherwise they'll precipitate out. So the spaces between these palladium particles is far larger than the particles themselves. So when you use that as a seed layer, the electroless forms rather sparsely, and it's not really a good conducting layer till it's, a micron or thicker. So that's the main difference. There's many other advantages of LMI, but this is the primary one that we're using for A-SAP. So there's a number of semi-additive processes, right? So there's A-SAP on the left, that's our process. And then in the middle, there's modified SAP, which is used a lot in things like iPhones or Android phones, things like that. So high-end consumer products that are pushing the state-of-the-art printed circuit boards, mostly manufactured in Asia. And they start with a thicker copper layer that's etched down to something around 5 microns. Typically, the control is not that great, so it might be between 3 to 7 microns, but that's used as the base copper layer in MSAP. There's another version of MSAP where you buy a fairly expensive ultra-thin foil, and the thin copper foil comes attached to a thicker copper foil that gets peeled off. So those are the two alternatives. Now, if you compare those to A-SAP, our base copper layer is far, far thinner. It's 10 times thinner than the ultra-thin foil. So when you try to etch away that base layer, which if you hit the down arrow, if this is the PowerPoint, it should animate here. And so in the process of etching away the base layer, you have not affected the electroplated copper at all in our case, or to an extent that is not really measurable. Whereas in the MSAP case, both of the MSAP cases, you are having some significant effect, which limits how small you can make your traces, and also, importantly, how small you can make your spaces. Okay, so on the left is A-SAP, that's our process, and on the right is MSAP, again, commonly used for high-end consumer products like cell phones. And the thing to see here is that these two images are at the exact same magnification. And so you can directly compare them. The M-SAP is about as good as M-SAP gets and about as good as it's been for several years. People are having a hard time pushing that to smaller feature sizes. We'll draw your attention to the base copper layer, which has not been etched off yet, and see how thick it is. It's a significant percentage of the total, and it would obviously have some effect. Etching that off would have some effect on the trace. You can see that the trace has about a 1-to-1 aspect ratio. It's about the same width, 27 microns, as it is tall, which is 25. And so that's about as good as it gets with M-SAP. In contrast, you see on A-SAP, and actually using semiconductor equipment, we've been able to get A-SAP down to even much smaller than this. But using, sort of the available printed circuit board type of equipment, at least the later versions of it, you can get quite good lines down to, say, 15 microns. In this case, it's 11 microns wide, 17 microns tall, and about a 14 micron spacing. You can see it also has near perfect vertical sidewalls like the M-SAP case. Really, that's defined by the lithography, the photoresist that was there. And you can see how thin that electroless layer is. Again, it's been left in place. It's just that bright squiggly line on top of the substrate. And you can clearly etch that off without having any significant impact on the trace. So that's how we compare to other semi-additive processes. Okay, and this is the final cross-section after etch. You can see that bright squiggly line has been removed. So the one key thing to remember here is that A-SAP is limited by the lithography tools that are available. And so those will get better over time. So not every printed circuit board shop will have the same level of lithography tools or the same expertise with using them. And over time, as they improve their lithography tools and they, naturally get better over time, A-SAP will continue to get better. So there's a question here about how does the adhesion of copper to substrate compare to standard construction for part stability and adhesion. There are slides on adhesion coming up, so I'll hold that question until we get there. So some of the design benefits first. Of course, one of the principal things is to shrink the size and weight. And that's really important because if you look at any modern electronics, it's really not the silicon that's occupying very much size or weight. It's all in the plastic and metal that connects the silicon together, the packaging, and probably more important, the printed circuit board. So shrinking those items is key to shrinking electronics overall. And of course, as I mentioned before, reducing the number of layers is a very good way of improving reliability overall, because in circuit boards, a big source of reliability problems are actually the vias. So if you can have fewer vias, fewer lamination cycles, you can improve yield, you can improve reliability. Signal integrity can be improved by this. For one, if you don't need the smaller feature sizes, let's say you have a controlled impedance line, its width is set by the 50 ohms that you need and the dielectric thickness, maybe it's 250 microns wide or something. Well, this can still help because of a couple of things. One, you can get exactly 250 micron wide line, or at least within a micron or so. Whereas, and with perfect sidewalls that don't change their slope. So you'll have a better controlled impedance line. There'll be less variability in that impedance over different boards and different panels and over the lifetime of the product. So that gives you back some of your budget for your signal integrity and your signal path by having better control of those controlled impedance lines. You could also do other things like broadside coupling due to very narrow spaces and high aspect ratios. You can get true differential lines and a bunch of other things, which we'll mention a little bit later as well. And so there are ways of improving signal integrity, improving RF performance. The one thing that people often bring up is that, well, if you have narrow lines, you get more insertion loss on a per unit length basis. And that's true, of course, or can be true. There are a couple of ways around that. One is by making high aspect ratios. You can get the line, even though it's very narrow, much thicker than it might be otherwise. And you can also try to shrink the length of the lines by putting components much closer together. That's actually the trajectory that CMOS has followed, right? CMOS has extraordinarily thin, narrow lines, and very lossy substrate, much more lossy than the substrates that you see in printed circuit boards. And there was a time when people felt CMOS wouldn't be good for frequencies above a gigahertz because of exactly those things. What the CMOS people learned to do was to model the traces much better, model the crosstalk, model the noise, model the insertion loss so that they knew what it was. But also, more important perhaps, is to just cram everything much closer together. So yes, you have more insertion loss per unit length, but the length is much shorter. And some aspect of that needs to happen in printed circuit boards. And we're actually starting to write white papers on some of the signal integrity stuff as well. And the biocompatibility advantages are really because we can make A-SAP and actually ASC is one of the leaders with us in working on this. We can make it out of entirely biocompatible materials. So instead of using copper for the trace, we can make the traces out of gold and platinum and palladium, and we can make the dielectrics out of LCP or polyimide. And so you can have and with no chrome or nickel or anything else needed to connect these metals to the substrates, so that you have materials which are don't cause any allergic or toxic reaction within the body, and in the case of LCP, don't absorb water and can stay happily within tissue for weeks or even months at a time. So how much miniaturization this is well, we mentioned the sizes before, and so A-SAP is really what's available today. And again, it depends on the lithography capability of the particular printed circuit board shop. We call A-SAP around 15 microns because if you've bought the latest, greatest equipment from Averatek, you can pretty readily get down to 15 microns. If your equipment's a little older, it's probably around 20, 25 microns. I think that's right where ASC is today, but we're calling it 15 microns as a technology. Over time, that will actually improve. But the present capability for most people that are using standard subtractive etch processing is about 75 microns. And that's, of course, 75 microns in the X, 75 microns in the Y. And then also the thickness of the dielectrics and the metals are affected by the minimum spacing. Because if you want to make controlled impedance lines, you have to have a certain thickness dielectric if your lines are a certain width. So going to MSAP, which is sort of what's the present capability for high-end consumer products like smartphones, you can see that it goes to 25. And that's not a 3x improvement. It's a 9x improvement in area and close to 27x improvement in volume. And the Averatek A-SAP process can meet or exceed that, depending on the lithography capability. What we're working on in-house on our roadmap technology gets us down to below 5 microns and also allows you to directly embed bare die. So that's probably 18 months to 2 years from being released. We are making prototype products in that now. One of the primary benefits you get from having more density on a given layer is being able to connect to very high density BGAs. And so this is an example where there's a BGA with 2,500 connections, a 50 by 50 grid. And just for the purpose of this analysis, we've simplified it. We've assumed every single one of those 2,500 is a signal connection. So no power, no ground. That's actually a worst case, right? Worst case for a number of reasons, but certainly for connectivity. And if you needed to connect to that and you had a 3 mil, 75 micron process with trace and space, you would need 12 routing layers to get all 2,500 connections for a 0.5 millimeter pitch. If you were able to go down to, say, 19 or 20 micron trace and space, you could do all 2,500 connections in 2 layers. And that's not looking at all the crosstalk issues or other things that might come up, but you can see that there's a dramatic difference based on how many tracks you can put between pins here. This is an image that we got from the Navy. The Navy is one of our licensees. They've got a facility in Crane, Indiana. And they were etch limited at first, subtractive processing. You can see that 75 micron spiral on the left. They had a MIVA, they do have a MIVA lithography tool that had both, I think, a 25 micron head and a 10 micron head on it. They were able to get down to 25 microns within the first few weeks of having our process. That's 9 times, area density. And then they tried out their 10 micron head, which they'd never been able to try out before, and it worked fine. They got down to 12.5 microns, which was the smallest feature size they had on that design. And that's 36 times density improvement for them without them spending a bunch of money on expensive new lithography tools or other capital equipment. So, they already had spent that money on the capital equipment earlier, just weren't able to leverage it. So I think I've mentioned a lot of these things before about vertical sidewalls, precision. So it's not just a matter of being able to make things small. It's a matter of being able to make them precise. And so that applies to large structures too, right? You can have a large structure, but have it very precise in terms of repeatability from one board to the next, 1 month to the next, right? So that's an important aspect of this. And of course, by relying on the lithography, which is the most tightly controlled part of the process, we gain that advantage. And of course, you need to be compatible with a lot of ultra high speed, low loss materials. And A-SAP is that. And I think the next slide addresses those materials and adhesion. Okay, so this should be an answer, at least a partial answer, to the question that was asked by Nathan Hirschfeld earlier. Okay, so these are some of the materials that we've tried out and have shown to work. So typical peel strength that's considered acceptable by most people is 4 pounds per inch. And so you can see that in the right column, this the peel strength listed in pounds per inch. The items on the left are those typical materials going from sort of normal FR4 materials to mid-loss, to low loss, to very low loss materials. And we expected that the peel strength would decline sort of precipitously to some extent, but it didn't, and that's fortunate. So even on the very low loss materials, the peel strength can be quite good. One of the reasons we expected the peel strength to get worse is because the surface of those materials is smoother. And the surface of the materials is really dependent on what base foil was there before we removed it and applied our electroless and electroplated copper. Because that base foil is gone, but the roughness that it left in the dielectric is still there. So you can see that we're listing what the base foil was for that purpose. So you can see what the original roughness of the surface was. And you can see that even in, we're getting well above 4 in most cases for even the very low loss materials. Some of the other surprises here is if you look in the right column, the PTFE for the Rogers 3003 and the CLTE-AT, the adhesion is so good that we actually can't measure it. We're listing it here as greater than 15, but the metal has not peeled off the Rogers material. It's actually ripped the Rogers material at 15 pounds. And in some cases, we're measuring 20 pounds peel strength there. And another surprise is the fast rise from Taconic, which has both a shiny side and an RTF side. We expect the RTF side to be fairly good, and it is, it's acceptable. But the shiny side really is never meant to be plated, and it's quite smooth, and which is what makes it shiny. It's probably less than 1/10 of a micron in roughness, and we're still getting really good adhesion there. So that's a very interesting data point that we're following up on. We can work with a few polyimides, especially the thermoplastic ones like Paralux AP and the some of the others that are out there that mimic that product from DuPont and Panasonic. LCP works really well. BT resin works pretty well. And then the build-up films like the Ajinomoto AFT films like the GX92 and GL102. On most of those, we can get 4 pounds or close. The 2.6 that you see there on the GL102, we were worried about that until we talked to Ajinomoto, and they said that basically nobody's getting anything better than that. And in the packaging industry, which is where that's mostly used, they accept that as an acceptable level of adhesion. So anyway, that covers both the materials and some of the adhesion effects. Basically, anytime you're looking at a new material, the primary thing to look at is the adhesion. And so we are constantly looking at new materials as our ASC. And if you have a material in mind, we can try it out. So to measure peel strength, you can see the chart there at the left where that's measured. It was measured at that shows 1 pound, but it's probably a 1/6 of an inch wide or an 1/8 of an inch wide. So you have to multiply it by whatever that number would be, either 6 or 8 or something larger. And you can see what the numbers are. We usually measure a few dozen peel strips and then plot them, and we get the averages and the ranges there. You can see here we've shown the Megtron 7N, the Rogers 3003, the Meter Wave 8000, and the Philios from Panasonic. So they're all well above 4 or 5, in some cases much higher. Okay, so I think we're going to switch to some characteristic impedance things. And the whole goal of this, and I don't want anyone's eyes to glaze over because there's some few equations going on, but the whole point of this little thing is to show that precision is important when you get to smaller feature sizes. It's not just about the small feature sizes, and that the narrow lines and thin dielectrics go together. So you can start sipping your coffee if that's enough for you. But let's start with characteristic impedance. So this is all about controlled impedance lines, and characteristic impedance is basically voltage over current. You can represent that in a number of different ways. And depending on the model of the transmission line, you end up with 4 low loss lines, which is virtually everyone that we're talking about. Basically just the inductive impedance over the capacitive impedance, which in the end is the square root of L over C. So, and the thing to think about here is that L is really a weak function of spacing, while C is a very strong function of spacing. So you can remember that when you're designing characteristic or controlled impedance lines. And so this is, if you want to make a 50 ohm line and you have a dielectric which has a decay of 4, then the width of the line and the thickness of the dielectric are pretty tightly correlated with each other according to this line. So for example, here, if you've got a dielectric thickness of 10 mils, you need the line width to be basically 20 mils wide. And on the opposite end of that, if the dielectric thickness is only 2 mils, then you need it to be roughly 4 mils wide. And so you have this curve that shows you that the dielectric thickness and the line width, for as long as you want to keep the impedance constant, it has this negative correlation, but close to linear, but not quite. And so at a given point, so you have some variability. You're trying to make a line. Let's say in this case, it's a 50 ohm line, you intended to be a 50 ohm line, let's say. So you made it 254 microns wide, which is the 10 mils wide, and over a 5 mil thick dielectric, right? So, but you're trying to target 254 microns wide or 10 mils, but you're not going to get that always. And this slope tells you how much impact you'll have on your impedance based on a change in your width. And you can see there that if the width changes, and unfortunately we're changing units here from plus or minus 5 microns, then you get almost half a ohm change in the impedance. Now, 5 microns is very tight for a normal subtractive process, but it's very loose for our A-SAP process. So we'd actually be quite a bit tighter than that. So you could stay well within, if the only variation was from the line width, could be well within, a quarter ohm of being within 50 ohms across all of your products that you're shipping, if the variations only came from line width. Whereas in a subtractive process, it's probably closer to 1 mil variation. John probably has a much better handle on that, but that would give you the full width of this chart. So you'd be, everywhere from 54 ohms all the way down to, let's say, 46 or 47 ohms. And this steepness of that slope is affected by how narrow it is. And that's maybe obvious, but if you have a 2 mil wide line and you're trying to stay at 50 ohms, you have to be much more precise about it, because a small variation in width is going to give you a much larger variation in your characteristic impedance. So as you use thinner dielectrics with narrower lines, precision is absolutely important, because that steepness of that curve keeps going up. So anyway, you might be wondering why you want to use thinner dielectrics, and there may be a number of reasons that are to do with the sort of the physical manifestation of the product as well. But one is that you just might want to put more density on a given layer, and so you want to use a narrower transmission line. In that case, if you want to stick with the impedance being the same, say 50 ohms, then you would have to use thinner dielectrics. You might want to increase the density of your vias, use smaller vias, and that also benefits a lot from having thinner dielectrics. And you might want to use much higher frequencies, and at some point this applies to fairly high frequencies, but you want to make sure that your dielectric is thinner than, say, 10% of a wavelength in order to avoid some of the higher order modes that you might get otherwise in the transmission line. So these are round conductors, but you can imagine them as rectangular. I couldn't find a good rectangular image here. One of the things I've been talking about is high aspect ratios. High aspect ratios are good for two reasons. One is, well, you just get more metal. You know, you might only be able to have it 25 microns wide, but you could make it 37 or 40 microns thick, or maybe 50 microns thick, right? And get back some of the resistance loss from having made it narrow. The other thing is that you can leverage the fact that the spacing is also narrow by having a very strong broadside coupling. And the broadside coupling, which you see there in the blue conductors in the middle there, they are a differential line where the current runs in opposite directions in those two conductors. And what that does is it pulls the current towards those edges that are near each other, because that's sort of, it's called a proximity effect, but it's really exactly the same phenomenon that causes the skin effect, which is causing current that is in the same direction to sort of repel each other and force itself to the outer surfaces. So anyway, you can draw current up against those inside edges. And those inside edges, remember, are perfectly smooth because they're defined by the photolithography. So you can leverage the full height of the conductor. You can leverage that smooth inner wall surfaces there as well. And you can get true differential behavior, which, if you've been designing in subtractive processes, it's virtually impossible to get a true differential behavior the way that most differential traces are designed today. So anyway, that's part of what we're going after. I think the next slide might show this in more detail or in a better way. Yeah, that's it. So this is a case, right? So these are copper traces on LCP, and the copper traces themselves are fairly narrow. We could have made them a higher aspect ratio. We probably should have for illustrative purposes here, but they're about 13 microns tall, 11 microns wide, so a little bit more than 1-to-1. And the spacing is about 17 microns. In this case, the spacing might have been a little smaller too to show that, but you can imagine these being maybe another 1.5 times taller and a little closer together. And if you had only two of them, and the nearest ground was all the way at the bottom, 100 microns away at the bottom of that LCP, or maybe 100 microns above at the top of another layer of LCP, those two would behave like true differential lines. Virtually all of their coupling would be between each other, as opposed to between itself, one of those traces, and the ground. Most differential traces that exist today, the vast majority of the coupling between either side of the differential trace is not to the opposite side, it's to the ground that's above or below it. And so you can get true differential line, which has a much better behavior in terms of radiating noise or being susceptible to other noise sources. I mentioned the biocompatibility advantages before. We're looking at a lot of different products from different OEMs, including glucose monitoring, neural probes, and other devices which are meant to be implanted. And so that's actually a strong suit. And ASC is probably our licensee and not probably, it is our licensee that's most advanced in this area. So this is sort of a recap of all the advantages. I hope didn't use up too much time here. But again, I think I've mentioned these already. I don't really need to say them again. So I think that's my last slide. Can we see what
it is?
Someone's asking, what about Teflon? So pure Teflon I don't think we've tried that. We've tried a lot of PTFE materials, like Rogers 3003 and others, and we do really well there. But that's not a pure Teflon. I don't know what you mean by Teflon. I'm not sure pure Teflon will work that well.
Haris, and we are in the process of evaluating several other materials. I'm not certain if we'd call them the older traditional high PTFE type products. I believe the gentleman may be referring to something like 5880 or a GX GT type material, something in the 90 something range to 70% range PTFE. We can certainly include those types of materials to get data. Traditionally, they've used fairly aggressive tooth structure, so hopefully we wouldn't have any issues with coating and adhering to those substrates. But again, it remains to be seen.
Yeah, and you can make all kinds of theories about why it should or shouldn't, but the easiest thing to do and the most reliable is just to try it out.
Exactly, and that's exactly what we plan to do. Well, thank you very much, Haris. Thank you for taking care of those previous slides. I didn't mean to surprise you there.